Good, eve- Good evening, guys. I'm Shreyansh Srivastava, and today we will be discussing about superscalar architecture and super pipeline architecture. So, first of all, let us start with what is pipelining and know a few basics of pipelining. Pipelining is a technique used in CPU design to improve instruction throughput by dividing the execution process into multiple stages, just like an assembly line. Each stage handles a part of instructions such as fetching, decoding, and executing and writing back. While one instruction is being executed, another can be decoded, while another can be fetched, all at the same time. This overlap increases instruction flow without increasing clock speed, making it a foundational performance enhancement. Now, let us move on to superscalar architecture. Superscalar architecture builds on pipelining by enabling the CPU to fetch, decode, and execute multiple instructions per clock cycle. This is achieved using multiple functional units within processor. Superscalar processor identifies independent instructions and issues them in parallel. To achieve this, complex control logic is used to analyze dependencies and schedule instructions dynamically. Now, let us move on to super pipeline architecture. Super pipeline architecture involves increasing the number of pipeline stages by breaking down existing ones into smaller substages. This allows the processor to operate at a higher clock frequency as each stage performs less work. With more stages, more instructions can be in flight, improving the throughput, but it also introduces new challenges in managing delays and mispredictions due to longer pipeline. Now, let us have a brief comparison between the two architectures. In pipelining, instructions are processed in sequence but overlap in time. Superscalar CPUs go further by executing multiple instructions at each pipeline stage, while super pipeline CPUs extend the depth of the pipeline to run at faster clock cycles. Superscalar focuses on parallel instructions execution, while Super Pipeline focuses on instructions overlap at a finer granularity. Now, let us talk a bit about their effectivenesses. Superscalar designs can significantly improve throughput by completing multiple instructions in one cycle, but only when there are enough independent instructions. Super pipelining increases the instruction throughput by reducing the times of each pipeline stage, therefore increasing the number of instructions in process. However, both approaches can suffer if instruction dependencies or branches are frequent. Now, let us talk a little about clock cycle and pipelining stages. In superscalar systems, the clock cycle remains the same, but more operations occur within it. In contrast, super pipelining reduces the dependencies on the clock cycle by slicing the pipeline into thinner, therefore increasing the number of pipelining stages. Superscalar aims to make better use of time per cycle, while super pipelining tries to shrink the cycle per cycle. Now, we also face a few hazards and challenges when using either of them, such as control hazards, data hazards, and structural hazards. Superscalar processors must detect and resolve instruction dependencies quickly and accurately. Super pipeline CPUs are more sensitive to hazards because more stages mean longer penalties for stall or branch mispredictions. Managing instruction timing, synchronizing, and correctness becomes more difficult as complexity increases. Let us move on to a few real-world examples. In modern computing systems, these techniques are often combined. For instance, a processor might have multiple execution units working in parallel, while also having deeper divided pipeline for each unit. Here, the multiple units working in parallel is a superscalar, while dividing pipelines for each unit is super pipelining. So here we are using both of them together. The blend of these techniques help achieving high performance in general purpose and embedded processors alike. Modern CPUs combine superscalar and super pipeline architecture for optimized performance. Intel and AMD uh, heavily rely on superscalar designs to maximize their instruction throughput and parallelism. ARM microcontroller prefers super pipeline techniques for achieving energy efficiency and lower power consumption while maintaining decent performance. Now, at the end, let us discuss a few pros and cons of both the architectures. Let us start with superscalar architecture pros and cons. Its pros are is that higher instruction throughput, parallel execution boosts performance, and good use of available resources when code has independent structure. Whereas it has a lot of cons too, such as complex hardware dependency and dependency checking and scheduling, diminishing returns with limited instruction level parallelism, and power hungry and expensive to design and verify. Whereas super pipeline architecture, on the other hand, has fewer pros than superscalar architecture, as higher clock speed is possible in it, more instructions in flight increases CPU utilization, and less complexity compared to superscalar in terms of resource management. It has a few cons too, such as sensitive to branch penalties and pipeline hazards, required precise synchronization between stages, and increased penalty during pipeline flushes. Let us talk about the conclusion we received from it. Superscalar and superpipeline architectures both aim to increase CPU performance but approach it differently. One through parallel instruction execution, the other through finer instruction staging. Both bring increased throughput and speed, but also introduces new level of complexity and hazard management. Depending on the application, one or both strategies may be used to achieve optimal performance. With this, I wrap up. Thank you. Both on thank you and have a nice day.